Good evening, everyone. Welcome to the week 5 live interaction session for the course Technologies for Clean and Renewable Energy Production. So, as usual, let's just wait for a few minutes for others to join before we begin our session for today. So, let's start our session for today. Let me just share my screen. I hope my presentation is visible and I'm audible. So, welcome to week 5 live interaction session for the course Technologies for Clean and Renewable Energy Production. This course is offered by Professor Prasenjit Mondal sir from the Department of Chemical Engineering, IIT Roorkee, Uttarakhand. Under the NPTEL SWI program, myself, Prasanjit, a PhD scholar from the Department of Chemical Engineering, IIT Guwahati. Myself as a TA, I conduct live interaction session for this course in this particular July to November 2026 semester. So almost 50% of the course is completed. We have come across 4 weeks and today we enter into the fifth week. To be very specific, the fifth week is also completed. So far we have learnt about different types of energy production, and then we have discussed about the use of petroleum and crude oil and other resources as energy sources for as energy resources. So in line with that continuation, today we will talk about gaseous fuel and syngas production. So gaseous fuel as such it just means that it just means that the gas actually burns with air to basically produce energy. And there are several applications of gaseous fuel. So in case if anyone who remembers what are the applications of gaseous fuel, where are gaseous fuel actually applied?
In LPG.
Yes.
We apply like LPG gas.
Could you just please be a little bit loud? Hello?
Sir, it is
Just a second.
LPG.
LPG, yes. LPG is one place where this gaseous fuels are used. So basically, the LPG comes under the category which is actually produced from petrol. So apart from that, there are also other kind of this gaseous fuel like syngas itself is a gaseous fuel, and apart from that, you have natural gas. So in that natural gas, you have LNG, liquefied natural gas, compressed natural gas, and then from solid fuels, you have water gas, producer gas, and somebody rightly said LPG, refinery gas, and also there are other types of gases like biogas and which are actually produced from the biomass. So this gaseous fuel, so in order to characterize, just like how we saw in case of the liquid fuel, similarly in case of gaseous fuel also we have certain characteristics properties through which we can actually learn more about the use of a particular gas as a fuel. So the gaseous fuel need to qualify certain criterias, or it has certain characteristics which needs to be good for them to be used as a energy efficient fuel. So we will discuss about around 5 to 6 properties. So the very first, so few of them we had already discussed in the previous sessions. So now we will just have a look at a few of them. So as such, when we talk about the properties of the gaseous fuel, we need to look after properties of gaseous fuels. So you need to first look at its composition. I mean, so the gaseous fuel may be composed of many different types of gases. So first we need to have an idea on the composition. So because the major reason being is that the few gases in this gaseous fuels or in that mixture of the gases may actually be inert. They will not be actually contributing to the energy production. For example, nitrogen gas. So nitrogen gas is very abundant in nature. So because of that, what actually happens is they, even though they may be a part of the gaseous fuel, but they may not be directly contributing to the energy or the calorific value of the fuel because they are typically inert. So composition of the gas is important. Second is the HCV and LCV value, which is the high calorific and low calorific value to obtain what how much will be the maximum amount of energy that can be obtained from the fuel, and what will be the least amount of energy that can be obtained from the fuel. So CV is nothing but calorific value. Then you have density and relative density. So density becomes an important characteristics for the gaseous fuel, because if it is highly dense, then transportation will become an issue. So that is directly linked to the cost that is involved in the process. So a heavier fuel will basically require more transportation costs, which basically makes it difficult for transportation, and that increases the cost of transportation compared to a low dense fuel. So density and relative density as such, when we mean, we basically compare the density of the fuel or of the gaseous fuel to the density of air. So the parameter density becomes important because it is directly linked with the cost. So as such, I think I have previously also discussed, in any engineering process, our main aim is to basically reduce the expenses that is involved in the process. Any design needs to be efficient, not just in terms of its energy, but also in terms of its cost, so that the profit margin can be appreciable. Then we have something called as UB index or UB number, you can also say. Then, so UB index is nothing but it indicates the interchangeability of the fuel gas, and it is typically defined with the formula. Just a second. UB number is equal to gross calorific value by the relative density whole power 0.5. So this is the definition of UV number. So UV number is nothing but it is gross calorific value of the fuel divided by its relative density to the whole power 0.5. So it basically indicates the interchangeability of the fuel gases that can be used. So there are typical examples of this UV, and it is usually measured in millijoule per meter cube, and there are typical values of this UV number for certain fuels. So one is methane, which is 55, propane, which is 78, natural gas, which is 50, and town gas, which is 27. So for any two fuels which basically have same UV number with the similar valve settings and given pressure, the energy output that you're going to expect from these two fuels is going to be same. So two fuels with similar V number will give similar energy output, provided that the valve settings and then the pressure is same. So this is about the concept of UV number. It typically determines the interchangeability of the fuel gas that you can actually use in a system to produce the energy. So it is typically defined as the ratio of the gross calorific value to the relative density of the air. Next, what we have is the temperature due, temperature of due. What is actually due? I think this due term is usually is a common term. Majority of us have understanding of due. What is due? Dew point. We typically refer to this word or commonly come across the word dew in weather forecasts. So what does this dew actually indicates or points to?
Yes, sir. Did you tell anything?
Yes.
Did you tell anything to us?
I cannot actually hear properly. So it is nothing but it is basically the amount of moisture that is actually going to be in your air. So in weather forecast, when we say dew, the word dew typically refers to the measured water content. Similarly, in case of the gaseous fuel, the word dew means the temperature. What it exactly means is the hydrocarbon mixture that or the hydrocarbon gas, the gas fuel that you are going to take is going to be rich in hydrocarbons. So that gas, when it actually starts to condense, that point is called as a dew point, and then the temperature at which this happens is called as the temperature of dew. So dew in case of the gas industries or gaseous fuels, it typically means the hydrocarbon rich, the point of the point at which I write it, that is the point at which hydrocarbon rich gas mixture starts to condense, and the temperature at this point is called temperature of dew. The condensation point of the hydrocarbon rich mixture, a hydrocarbon rich gas mixture to the water, to its liquid form, that point is called as a dew point in case of these gaseous fuels, and then the temperature is called as the temperature of dew. Then another property that we have to look at is the exposability limit. Exposability limits. So here we need to know that for burning of any kind of substances, three things are actually very much important. Can you name what are the three components that are important for starting a fire anyway? Like without these three
There
things,
must be present of oxygen.
yes,
Present of oxygen. Present of oxygen. Sir, it is present of oxygen.
Yeah, presence of oxygen is one. Apart um, two more what do you say parameters which is involved. If these two are not there, then also you cannot actually start the, I mean, burning will not start.
There must be fire. Without fire, it cannot occur.
Basically temperature. So temperature is one. Then another thing is, as someone rightly said, oxygen. Then another one more. It's going to be a fuel. I mean, there should be a source, right, for the burning. So that source, that is the fuel. Apart from this, you also basically, for the ignitions to start, there are also three things that will be required. One is the time, temperature, and turbulence. So here, in case of the exposability limit, we have two different parameters. One is LEL and another one is UEL, that is lower exposability limit and upper exposability limit. So lower exposability limit is nothing but the minimum concentration of that combustible gas which is necessary to support the combustion in air. So what will be the minimum quantity of the fuel that will be required so that the combustion can actually start? So that particular parameter is called I mean, is characterized as exposability limits, and it has two range, or it actually exists between these two ranges as LEL and UEL, lower exposability limit and upper exposability limit. So this limit is typically characterized by the oxygen to the fuel ratio, or it's usually set by the oxygen to the fuel ratio. Apart from this exposability limit, we have something that we discussed prior also, called as octane number. Anyone who is able to recollect what is octane number? Octane number. This is something that we discussed even when we were discussing about the liquid fuels, if I'm not wrong, or the crude oil characteristics. If you remember, in crude oil characteristics, we discussed about two different we discussed many parameters or characteristics. Among them, octane numbers, cetane numbers were few. So now, even in case of the gaseous fuel, we have to discuss about the octane number. So what exactly is the octane number represents or signifies, like what it indicates? So octane number basically represents for the engine's knock resistance. So depending on this, whether a fuel should have higher octane number or should it have lower octane number for it to be characterized as a good fuel. Engine's knock resistance. So just find out which is the better fuel. Fuel having high octane number, or B, fuel having lower octane number. And of course, why? So please find out the answer to this question. Now, these are the 7 characteristic properties of the gaseous fuel that we need to basically keep in mind, or we need to analyze to characterize whether a particular gas is a energy efficient fuel or can be used as an energy efficient fuel. Now, these gaseous fuel, their application is, as you know, so these gaseous fuels, I mean, the major reason is why we are interested in learning about the gaseous fuel is because they are used for the energy production. So either they are directly used for the production of energy, or they are also, or they can also be used to produce some other form of chemical which can be used for the energy production. And that's what we are actually going to check. So either use them directly for the energy production or the electricity and heat generation, or use these gaseous fuel, convert them into some form of other compounds or chemicals, and use that chemicals as an energy resource. So that those particular stuffs we will be discussing now. So again, when you are going to talk about direct heat and electricity generation, there's nothing much that we have to talk about. Whereas we will be particularly more interested in discussing about how to use these gaseous fuels and then convert them into different kinds of energy resources, or you in different form of different compounds, and then use those compounds for energy resource or as an energy resource. So that first thing that we will be discussing is nothing but it's the reforming operation. I hope the slide is visible. Reforming operations. So in reforming operations are nothing but the natural gases are typically converted to carbon monoxide plus hydrogen gas by either exothermic or endothermic reaction. So there are multiple different reforming process. So reforming process as in what it means is you take this natural gas and then convert this natural gas into into a mixture of carbon monoxide and hydrogen, CO plus H2. So I hope you remember CO plus H2, that combination, that mixture of gas is also called as a synthesis gas, or in short syngas. And this happens if you use oxygen. In case of oxygen, if you are going to supply air, then the presence of nitrogen is going to be there in the product gas mixture. So then the synthesis gas is also called as the producer gas. I hope you remember the difference between synthesis gas and producer gas, which we discussed, I think, quite a few lectures before. So in synthesis gas, you have only carbon monoxide and hydrogen gas, whereas in case of producer gas, nitrogen is also going to be present, because the combustion or the gasification process happens in the presence of air and not in the presence of oxygen. So in case of air, the nitrogen contribution is going to be there, and since nitrogen occupies almost 79% of the air, the product stream, and also it's going to be inert, so in the product stream as well, the nitrogen gas will be present, and then the entire gas mixture is going to be called as a producer gas. So coming to this reforming process where this carbon monoxide and hydrogen gas is produced, this production of natural gas to syngas or conversion or transformation of natural gas to syngas usually happens through either exothermic or endothermic reaction. There are several different processes through which you can actually obtain this syngas. So the first one is steam reforming, dry reforming, then you have this partial oxidation reforming, then you have autothermal reforming. So these are the 3 or 4 most commonly and widely used process. If you see your lectures, then it is mentioned that steam reforming, partial oxidation and autothermal refining are the widely used process. Apart from that, there are several other processes, but those are not very commonly used for different performance related issues. But however, they are good in emitting low amounts of greenhouse gases. But however, in case of the industrially accepted or industrially widely used processes, steam reforming, partial oxidation and autothermal reform. All these kind of reforming operations basically vary depending upon what you use as a reactant. So suppose if you see in all these cases of steam reforming, partial oxidation and autothermal reforming, in all these cases, the methane is going to be used as a hydrocarbon source, CH4, and then the only change happens in the kind of fuel or the you cannot say fuel, in kind of the other reactant that is you're actually using. In case of steam reforming, you are actually going to send in steam to basically convert your methane into carbon monoxide plus hydrogen gas. Whereas in case of the partial oxidation, you are actually going to send in oxygen. However, it's not going to fully oxidize. It's not going to be a complete conversion. Whereas it's going to be an incomplete conversion. That is the reason it's called partial oxidation. You're not going to completely oxidize the mixture. So that is the reason you are actually ending up with the carbon monoxide. Because if you happen to send in stoichiometric quantity of air, then the CH4 may be converted to CO2 and H2 or H2O rather than converting to CO and H2. So for that you basically supply less than the stoichiometric air requirement for the conversion of methane into carbon monoxide plus hydrogen gas. If you come to autothermal reforming, over there you typically use both water or steam as well as the oxygen to basically convert CO2 to convert CH4 to carbon monoxide and hydrogen gas. So if you, and in case of dry reforming, you do not send in steam or oxygen, whereas you send in carbon dioxide itself to form carbon monoxide and hydrogen gas from methane. So it's only the process that is actually going to be different, but then the amount of but then the product stream is going to be composed of only two types of gases. One is CO and another one is H2. H2, sorry, hydrogen gas. So just a second. So if you see, you can check the other details in case of, so what would be the temperature ranges? Like for example, in case of steam reforming of methane, the temperature usually varies between 970 to 1100 Kelvin or 1100 Kelvin. Whereas in case of partial reforming, you require much higher temperature range. Whereas in case of autothermal reforming, it somewhere lies between your steam reforming and partial oxidation. And similarly, you can also look at the pressure ranges. And you can also see that the H2 to CO ratio typically varies between 3 to 5 in case of steam reforming. That is, more amount of H2 is actually going to be generated in case of steam reforming compared to that of partial oxidation, compared to that of the autothermal reforming process. So Each of these process has their own advantage as well as limitations. And you can also see the enthalpy of the reaction. In case of steam reforming, it's going to be 206 kilojoule per mole of energy. Whereas in case of partial reforming, it's going to be minus 36. So it's going to be an, so if the delta H value is negative, is it going to be an exothermic reaction or an endothermic reaction? Delta H.
Endothermic reaction.
Do you say exo or endo? I couldn't
Sir,
get.
it release heat. Sir, it release heat.
Okay.
Heat release होगा sir.
Okay. I couldn't get it actually. I'm really sorry. So then comes the bi-reforming and tri-reforming process, as you can see here. So in this case, what actually happens is you use all these three processes together. If you see the tri-reforming, it's you use steam, carbon monoxide as well as oxygen in the process to generate carbon monoxide plus hydrogen gas, just to increase the enthalpy or the amount of energy that you can actually obtain from the process and increase the production of carbon monoxide and hydrogen gas. So this hydrogen gas that gets generated can be used as a fuel in itself. So it can be used in case of fuel cell as a hydrogen powered fuel cell, or it can be used in multiple different purposes. So the fuel cell is something that is more attractive these days. I hope you also have heard about the news wherein there is a now we have a fuel cell powered train. I hope you have heard about it. So in case if you not, you are welcome to you are welcome to go through the news articles out there. So so this hydrogen powered fuel cell typically uses hydrogen gas and oxygen as their fuel to produce the electrical energy and water as a product. So this electrical energy can be stored and harnessed for several different applications. So this is one particular most interesting application of hydrogen. And apart from that, there are several other commercially available commercialized process that are there. So kindly have a look at the hydrogen gas fuel production lecture slides in the week 5 course content. So this syngas, whatever we are talking about, that CO2 plus CO plus H2 can actually be used for the liquid fuel production. So we will be discussing about that now. So in case of the we try use syngas to basically produce many different chemicals. That's what I typically said. The gaseous fuels, either they can be directly applied for the energy generation, or they can be converted into some other form of chemical which can be used for the fuel, which can be used as fuel. So this syngas can actually be converted into three different components, or three different or can be converted to liquid fuel production through three different ways. So the first one is the Fischer-Tropsch synthesis, second one is the methanol synthesis, and third one is the DME synthesis process. Any idea on what is DME? DME. DME is nothing but dimethyl ether. So dimethyl ether can also be is actually used as a fuel because it is because it basically produce because it's a cleaner source of energy. It does not produces any kind of nitrogen gas NO2 kind of gas emissions, and so it's more clean and it's more clean in nature. So that is one of the main reasons why dimethyl ether is used as a energy resource. So typically the syngas production and utilization that process looks like this. So you either take a biomass or a waste, you do this gasification process. I hope there are no questions on what is gasification process. We did discuss about what is the difference between gasification, pyrolysis, and combustion. So in case if anyone has doubts, please let me know, or how to differentiate between these three different process. Anyone? So typically they vary depending on the type of product gas that gets emitted, which is nothing but it's a direct influence of the oxygen to the fuel ratio that we supply into the system. So in case of combustion, you actually supply with the excess of air more than its stoichiometric limit. In case of gasification, you supply controlled amount of oxygen, or you can also say the levels being similar to the stoichiometric quantity that is required for the burning. And in case of pyrolysis, you basically supply deficient amount of oxygen that is much lesser than the actual required value. So depending upon this, it affects the composition of the gas. So in case of combustion, you will have more amount of carbon dioxide, more complete combustion and oxidation. So more amount of carbon dioxide and water. Whereas in case of water or water vapor, whereas in case of gasification, since there is a controlled supply of air, you typically tend to have, apart from some amount of carbon dioxide, the carbon monoxide and hydrogen gas is going to be very dominant. They are going to occupy the major constituent of the air of the product gas mixture. Whereas in case of pyrolysis, it's typically going to be CO plus H2 and other form of carbon particles, solid particles are going to be present. So the biomass or the waste can typically be converted to syngas using this gasification process. This syngas, as we said, can be used for the liquid fuel production. One is through the Fischer-Tropsch synthesis. So that is basically used for the production of this naphtha, bags, and other kind of chemicals through several different chemical reactions. Then another thing that we have is these conversion of syngas into methanol, CO plus H2 to CH3OH. So that typically happens using a metal catalyst. So the metal catalyst that is used in this process is nothing but it's a combination of three different metal oxides: copper oxide, zinc oxide, and aluminum oxide combination. These three oxides are used as a catalyst for the transformation of syngas to methanol. This reaction typically happens at low temperature and high pressure conditions. So here if you see, the H2 to CO ratio is typically maintained as 2:1. So that is the reaction how it goes. CO plus 2H2 gives CH3OH. So the methanol is also another one kind of chemical which is can be used as a fuel for the energy production. It's an energy fuel, energy liquid fuel to be more specific. So apart from this CuO, copper oxide, zinc oxide, aluminum oxide catalyst, you can also use other catalysts such as chromium zinc oxide or zirconium manganese metal oxides. So, however, the one of the major problem, or you can say the limitations of this process is it's a low temperature but a high pressure process. So you need to you need to maintain high pressure in order for this transformation to happen. So, and to maintain high pressure, that again is linked with the cost involved in the process. So the best method as such, if you see, it's going to be a low temperature and a low pressure process. So for that, we basically go for two different strategies. One is nothing but it's your BNL method. Brook have a national laboratory method and methyl formamate method. So let me write this. So it's a low temperature and high pressure process. So there are also other alternatives towards converting the syngas to methanol. So the two methods are BNL method and another one is your methyl formate or MF method. So in both these cases of Brookhaven national laboratory method and in case of the methane formamate method, you take the CH4 and then you basically react it with the nickel catalyst or copper oxide catalyst with the alkoxide organic solvent. So the solvent that is used in this both these methods are alkoxide organic solvent, which is nothing but it is the triglycine, which is nothing but triethylene glycol dimethyl ether is used as a solvent along with the CH4 in the presence of nickel catalyst in BNL method and copper oxide catalyst in methyl formamate method. So these two methods are comes under the classification of low temperature, low pressure methods. So kindly remember this, the conventional synthesis process of, or you can say the conventional conversion of syngas to methanol is a low temperature, high pressure process. The modified methods are BNL and methyl formamide method, which is low temperature, low pressure methods. So this is one another way of converting the syngas to liquid fuel. The other process is going to be making dimethyl ether out of syngas. For that, we are going to use a catalyst, which is we are going to use a bifunctional catalyst, and in this case, the ratio between the H2 to CO is going to be 1, and that is what is going to generate dimethyl ether. So here the ratio of H2 to CO is going to be important. If more amount of hydrogen is going to be present, then the chances of the synthesis of methanol is going to be more compared to if the ratio is going to be low. However, there is also another one process of converting methanol to dimethyl ether, that is using a acid catalyst. So in even in that way also you can convert the methanol to the dimethyl ether, but that is actually going to be an indirect route rather than converting syngas directly to dimethyl ether. So all these kind of chemicals that we synthesize are used as a clean and a renewable energy resource, which can and as a renewable resources for clean energy production. So the major aim is to basically produce energy, but then that energy needs to have low environmental but it should be environmental friendly. It should not cause harm to the environment. Moreover, it should be environmentally sustainable. So that is something that is going to be of prime importance. We need energy, but that should not come at a cost of something. The amount of damage that we are going to do in the process of production of energy is going to be minimal. So that is the reason these um, cleaner fuels are actually produced, because if you're going to use directly this carbon monoxide and H2, they can also be used as a direct resources of energy, but they're actually going to pollute the environment. Carbon monoxide is a pollutant. So that typically, um, so that is not environment friendly. So we basically convert them into different kinds of fuel, and these fuels are actually going to be cleaner in nature. So then we basically use these clean fuel for our energy production. So that's how that hydrogen gas is also going to be used. Hydrogen gas is going to be used for different kind of energy, because hydrogen has a lot of potential for energy. Specifically, when this LPG shortage came few months back, the use of hydrogen gas as a potential energy resource was blooming at that time, and still there are people who think that as an alternative to the conventional liquefied petroleum gas that we use, owing to the lack of scarcity that we have and we were currently facing few months back. So to basically conclude this topic, so the thing is, majorly we need to produce energy, and we basically look at the different kinds of fuels. So previously we looked at liquid fuel. Now we are basically going to look at the gaseous fuel and how to use this gaseous fuel for the energy production. Either use them directly for heat generation or electricity purpose, or basically convert them into different forms of energy, or basically produce the different kind of liquid fuels from them, like methanol, dimethyl ether, or some other form of compound like naphtha and wax, and use them as a cleaner energy resource. So, any questions in this? Because the next session will be problem solving. So, before that, in case if you have any questions, then please let me know. Again, this is a brief overview. We have not discussed about the different kinds of reformers that we use and their specific designs and mechanisms, or the types of catalyst in detail has been covered in the lectures. So please go through the week 5 course content in case if you have not. There you will get more details about each of this process. This is a brief recap to be specific about, and basically we discussed only the important stuffs in the um, live interaction session. Because of time constraints, we have to finish everything within 2 hours, 2 hours 15 minutes. So please go through the course content. Any questions, anyone? So so in case if you have no doubt, then let's progress towards the next, I mean the MCQs. However, before that, just take a few minutes break, just a quick break for 5 minutes. So in case you have any doubts, so in case if you have any doubts, you're welcome to ask me, or the slides will be visible, so you can actually look at that and start answering the problems. And in case if you also want to make a comment, please go for it and be back in 5 minutes maximum. So the slides will be there on the screen. So for those of you who are okay, then kindly solve the problems that is visible to you on your screen. So I think we can start with the renewable. Just a second. I think so question 1. Which of the following, you can say gas, sorry, which of the following gas is in the correct order of their would be number? Is it town? I mean, the comparison is between methane, propane, and town gas. So, which of the following gases will be correct order of their would be number? 'I think I just said, told few values when we were talking about this concept. Anyone? It should be nitrogen. Yes, anyone? We just need to know the values of each. If you know that, then the answer is right in front of you. So I think it is better for me to give the value. So town gas, the value is 27. Units is megajoule per meter cube. For methane, it is 55 megajoule per meter cube. And for propane, it is 78 megajoules per meter cube. So with this value, I think you would be able to come up with the exact order for the UV number. So it should be propane first. Propane is greater than methane, greater than town gas. So option A. Any other answers? Just a minute. Anyone? Any other answers? So this is the order for their movie number. Next, select the current statement about the mine methane. Mining, that mine methane. If so, option A, it comprises of CH4 96% and N2 3%. The mining methane is collected in steel pipeline. Its content at 20 to 50 percentage depends on the applied pressure, and all of the above. About the mining methane, that mined methane. So we are supposed to state the correct statement. Any answers? Oh, option B. Okay. What about option A and C? Okay, this is fine. This is one option. So you say option A and option C is wrong. So correct statement is mine methane is collected in steel pipelines only. Yes. Any other answers? One of you have told option B is the correct statement about the mine methane. So the exact answer is all of the above. I'm going to mark this in some other color. So the mine methane is going to comprise of CH4 96% and nitrogen that is going to be 3%, and it's actually collected in steel pipeline, and its content air is 20 to 50 percentage depending upon the applied pressure. All the above are true about the mine methane. Moving to the next question. So I modified this question a little bit. I think something was missing. 1 meter cube of gas hydrate roughly has how much amount of methane? 1 meter cube of gas hydrate roughly has how much amount of methane content? Okay, thought some answer will. Any idea? So these are all exactly there in your course content slides. So please go through that. So in case, so if you go through that course slides in detail, you will be able to answer most of the questions comfortably. So the answer is 164 meter cube. So I hope nothing much, because these are all facts based questions. So I don't think there will be much doubt in this. So moving to the next question. Which of the following is not an efficient route for the hydrogen production? I told you, right? For there are multiple different ways to produce hydrogen. The question here asks this: which of the following is not an efficient way for hydrogen production? Decomposition of hydrocarbon, thermolysis of water, photolysis, and combustion of biomass. Thermolysis in the sense breaking of water molecule with the help of temperature, and photolysis is similar breaking in presence of light, photo. So lysis means breaking, and then the prefix over that basically describes as the process in which the breaking has occurred. Option C, photolysis. Okay. Is there any specific reason why photolysis is not an efficient route for hydrogen production? So read about this question, because the thing is with this question, it's actually exactly given in the lecture slides. You just need to compare about different process for hydrogen production and then let me know the answer. So I'm going to mark this question because I need to know why you are telling photolysis is not an efficient route for hydrogen production. Maybe, but why? I mean, reason, is it like more in terms of the amount of hydrogen that gets produced, or it's going to be more cost expensive? Let's go to the last question before we come to the second one. Which of the following statements is not true about methanol synthesis? Methanol synthesis is an exothermic. It is favored at low temperature, high pressure. It operates at 220 to 250 degrees Celsius. All statements are true. I think this is a much better. We discussed almost all the details. All are true. Correct. All the statements are true. The methanol synthesis is an exothermic reaction. It is favored at low temperature and high pressure. The temperature at which this process operates is usually 200 to 250 degrees Celsius, and then the pressure is 5 to 8 megapascals. And it's an exothermic reaction. Energy gets released in this process. So that is the reason low temperature and high pressure favors this methanol synthesis process. So all the statements are true. I hope no questions in this. Now come to the second question. The temperature required in non-thermal plasma cracking of methane. So basically the cracking of methane is done to produce the hydrogen gas. So in case of non-thermal, what will be the temperature that is required or that will be required? Is temperature required in the non-thermal plasma cracking of methane. So it is 350 to 750 degree Celsius. So kindly remember this. No, any answers? No. So let's move on towards the next one. So please remember the temperature that is required for non-thermal plasma cracking of methane is 350 to 750 degrees Celsius. Next, the fixed tubular reactor for methane reforming operations operate in the temperature range of dash and pressure range of dash. What is the temperature and pressure range in which this methane reforming operation happens in case of a fixed tubular reactor? Fixed bed tubular reactor. Uh, C, okay. Yeah, it is C. That is correct. So the fixed tubular bed reactor for methane reforming operations operate within the temperature range of 700 to 950 degrees Celsius, and pressure range is going to be 10 to 25 bars. So next question is overall reaction for partial oxidation reforming. So there are four different processes. You are supposed to let me know which is the exact process. So I think this is exactly from the, I can show the slide itself. So for partial oxidation, it's going to be half oxygen. So option A, the first one. So I think uh, Let's color this, and so it's going to be option A. The overall reaction is going to involve half of O2, that's going to release CO plus 2H2O. 2H2, sorry. So any questions? How did this come? Any questions here? Anyone? So far in this around 9 questions that, sorry, 8 questions that we discussed, any questions? Any doubts so far? If not, we can move to the next question. So moving to the next question, it's a problem. So calculate the UV index for a typical fuel. Gross calorific value of the natural gas is 1200 BTU, which is a unit of energy per feet cube, and its relative density is 0.65. One more important info: 1 BTU per feet cube is equal to 0.037 millijoule per meter cube. So with this data, you need to calculate the UV index for a typical fuel. So can you calculate and let me know the answer? I hope you know the formula. So How to solve or any answers so far? Okay, somebody has given answer. 0.14, sorry, 0.014 millijoule per meter cube. Okay. I think since I got an answer, I can start solving the problem. Hmm. Index is equal to gross calorific value upon relative density whole power whole power 0.5. So V index is equal to gross calorific value is 1200 times 0.037, the whole divided by 0.65 power 0.65 is the relative density. So that whole power 0.5. Now if you calculate the value, then calculate, let me just calculate it. So 1200 times 0.037 is 44.4. Just remember this value, 0.65 whole power 0.5. 44.4 by 0.806. 55 megajoule per meter cube. 55.08 megajoule per meter cube. Wait, just so what? So the exact answer is 55.08 megajoule per meter cube. Sorry, there was a connection issue. So let me just share my screen. So this is the answer for the problem. I mean, calculate the UV index for a typical fuel. So first you take the gross calorific value and then you convert that units from BTU per feet cube to megajoules per meter cube, and then you basically take the relative density which is given as 0.65 to the whole power 0.5, which is comes out as 55.08 megajoule per meter cube. Any other answers? Because I did see a different answer being somebody had given a different answer, but I think since the call got disconnected, that particular answer I cannot see. So if you have obtained any different answers, then please let me know. So then in that case, shall we progress to the next question? Oh, okay, let's move to the next one. So this question is not related to this week's course content. So this is something that was what was there, but we were not able to solve in the last live interaction session. So we will solve that now. So the question goes something like this. It is required to decoke a visbreaker oil which has an inside dia as 10 centimeter, and it's going to be 1000 meter long with a coke layer of 0.25 centimeter thickness. This is going to be done in two steps. One, air is introduced to combust the coke layer whose density is 1200 kilogram per meter cube, and then the steam at 550 degrees Celsius and flow rate of 1500 kg per hour is introduced to the coil to remove debris and cleaning up. The exit temperature is given as 650 degrees Celsius. Coke contains 90 weight percentage of carbon and 10 weight percentage of sulfur. So how long should the steam be switched on in hours? So you are supposed to decoke a visbreaker oil, and that is going to happen inside an equipment which whose diameter, inner diameter is 10 centimeter, and it's going to be 1000 meter long, and then the coke layer is 0.25 centimeter thickness. It is going to be done in two steps. First, you introduce air to combust the coke layer, then steam at a particular flow rate is introduced to remove the debris and cleaning up. The product is at 650 degrees Celsius, and the coke contains 90 weight percentage carbon and 10 weight percentage sulfur. For how long you need to keep the steam switch on in hours for this process to complete? How to solve about this problem? Anyone, any idea on how to solve this problem? Okay, I'll show the question. So this will be the final question for today's session. So once we solve this, we can wind up. So I need to give few values. Let me give that. So I think with that it would be, so specific heat of steam, you can take it as 2.13 kilojoule kilojoule per kg degree Celsius, and enthalpy of carbon combustion, or you can say heat, version is 32,770 kilojoule per kg, and heat of sulfur combustion is 9,300 kilojoule per kg. So with this, you are supposed to calculate how long should the steam be switched on for the process, or for the combustion to occur. So if you have any answers, you're welcome to let me know, or I think I can progress to solve the problem. So first we need to estimate the volume of the coke. Volume of coke layer is going to be equal to pi dl times its thickness. So area times thickness, so area is pi dl times thickness. So 3.14 times, dia is in centimeters, so I'm converting it into meters, times, so 10 centimeter is 10 by 100, so 0.1, times length, that is 1000, times uh, thickness, which is again in just a second. So that would be 0.025, right? Yeah. So now this value is 3.14 times 0.10 times 1000 times 0.025, 7.85 meter cube. Now we know density. So density is mass by volume. So mass is nothing but density into volume. So mass of coke is density 1200 times 7.85. 9420 kg. Now with this, we need to come to the next question where it is written that the coke contains 90 weight percentage of oh, here there's a mistake because 0.25 by 100, so this would be 0.785, so this would be 942 kg. So now we are supposed to calculate what will be the heat that gets generated from this particular amount of mass of coke. The heat of carbon combustion is going to be equal to 0.90 times this enthalpy that I've given, 32770, times 942. Similarly, heat of sulfur will be heat of sulfur combustion is going to be equal to 0.10 times 9300 times 942. So what is the value? So 32770 times 0.9 times 942. It is going to be 277,82406 kilojoule, and then this one is going to be 942 times 930, 876,060 kilojoules. Now total heat, that is the heat that you get from carbon as well as sulfur combustion, is going to be the addition of both. Going to be 2 point or like 286 58466 kilojoules. Now this will be the total heat that gets generated. Now the amount of heat that is gained by the steam, is mcp delta T. Am I correct? It's going to be mcp delta T. So m is given in the form of mass flow rate. So 1500 kilogram per hour times 2.13 is the specific heat of the steam, times the temperature difference, that is 100, which is nothing but 319500. kilojoule per hour. Now, if you divide these two, you will be able to calculate for how long you are supposed to keep the steam on. So, total heat divided by heat gained by the steam is going to be equal to the number of hours to keep the steam on. So that would be, so time is equal to 28658466 divided by 319500. 89.69 hours. Just a second. Yes. So for these many hours, you need to keep the steam on so that you can get the required amount of heat that get heat from the system, or the steam can be used for the combustion. Any questions in the way we went with the calculation? Anyone? Okay. If there are no doubts, I think I can stop presenting the screen. So in case if you have any doubts, please let me know before we conclude our session for today. Okay, so thank you all for joining today's live interaction session. Our next live interaction session will be on 30th of August from 5 p.m. to 7 p.m. I hope to meet you all there. So I take this as an opportunity to thank Professor Prasenjit Mondal sir as well as the NPTEL team for providing me this opportunity to interact with you all on this Sunday evening. So thank you for joining today's live interaction session, and I hope to meet you all in the next one. Till then, have a great weekend ahead, and keep continuing to work on your course. Thank you and bye.